This is something I'm very seriously trying to understand. When I say work in progress, I don't just mean I'm writing it. I'm trying to figure it out. And so I look forward to discussion here about it. MacLean is Aristotelian. I'm not denying he's a Platonist. This is not arguing against Bartek's position. For one thing, I'm not very concerned. Well, there are two reasons. One is I'm not particularly talking about his ontology. I'm not saying it's an Aristotelian ontology. The other is I'm not very concerned to classify MacLean at this point. I'm concerned to draw out some similarities and see what we can do to understand them. Also, of course, I'm constantly being asked, I write these papers on philosophy of math, and they have symbols in them. And so people say, well, how can that be philosophy? Because there's a symbol. And I want to explain how it can be philosophy. I'll start with Aristotle. To me, this is a very persuasive depiction of Aristotle, but these are all made up. We have nothing that we can consider accurate representations of what any people from that time looked like. Aristotle says, we do not think we know a thing until we are acquainted with its primary conditions or first principles and have carried our analysis to its simplest elements. And here, by know, he means have, some translators say scientific knowledge of. That's, I think, a bad anachronism. He means really know. And here he's aligned with Plato. I mean, I might know how to find the hotel from here, but that's not the knowledge he's talking about. We don't really know it until we have done this. Now, understand simplest here does not have to mean what current philosophers call foundations. That's not necessarily the direction that we're going. And he tells us, I think this is very important, the natural way of doing this is to start from the things that are more knowable and obvious to us and proceed towards those which are clearer and more knowable by nature. Did I have a comment on this? Yeah, okay. But I don't understand why he thought this. I mean, I look at the history of physics and I say, this is exactly what happened. At first you think there's earth and water and air because you can see those things. And then you decide, no, it's sulfur and mercury and acids because those are more fun. And then you say, no, it's phlogiston and the sources of phlogiston. And then you have, no, it's the chemical elements. I mean, we see the history of theories of matter going from what's knowable right around us to what's, in one sense, harder and harder for us to know, but in another sense, easier and easier for us to know. I have not learned the standard model of particle physics, but the people who have can use it to successfully explain the behavior of matter at a level that was impossible before. It turns out the standard model of particle physics is more knowable by nature than any previous theory of chemical elements or matter. And I don't know how Aristotle knew that at the time when none of the sciences had been through that progress yet. But he tells us that. Well, he thought it because he wrote it down. Or somebody wrote it down and put his name on it. And I want to call these Aristotelian naturalism in science. The sort of three tenets. Philosophy is the pursuit not of facts but of knowledge. Now, of course, everyone will agree that philosophy is not accumulating lots of facts. But I do want to stress that for Aristotle, knowledge, even of sea creatures, let alone knowledge of the constitutions of cities, is philosophy, paradigmatic philosophy. Philosophy is about those. The special sciences are parts of philosophy. They are loves of wisdom. For Aristotle, unlike for Plato, or at least differently than for Plato. We know a thing when we have found its elements and simplest parts, whatever that means. We begin with what's more knowable to us and move to what is more knowable by nature. Of course, I mean, there's an obvious comparison here with category theory because any number of people over the decades have assured me that they don't understand category theory, as if this was an argument. Well, okay, they don't, but that's how knowledge advances. So this is, I believe that Penn-Matty has done a really good job of spelling out some concept of naturalism, spelling it out in detail and seeing how it applies to a particular enterprise, really the cabal theory, trying to solve the continuum hypothesis. I like Penn's work on naturalism a lot, but I think we need to broaden the discussion and take seriously what it could mean. And this is what I'm going to call Aristotelian naturalism. And I really want to stress the same things are not knowable relatively to us and knowable without qualification. I hope everyone here understands that when Zermelo first gave his axioms for set theory, very few people said, oh, of course, that's what I've been thinking all along. They were surprising. The whole idea that there's an empty set. At one point, it was considered obvious there can't be an empty set because a set is a set of things, and an empty set doesn't have things in it. This was considered a serious objection at one time because people hadn't thought that way. But today, it's pretty standard stuff. For MacLean, these two questions were inseparable. We can ask, what are mathematical objects? How do we come to know them? I mean, I guess this is a paradigmatic philosophical question about mathematics. What are the objects? How do we come to know them? What are solutions to a partial differential equation, and how do we come to know them? For MacLean, these are not two different kinds of questions that belong in two different departments. The second is just a special case of the first. Whatever answer you give to what are solutions to a PDE has got to include some concept of what are mathematical objects. And how do we come to know the solutions has got to include some concept of how we know mathematical objects in general. Say, question 2 can only be a special case of question 1. They are not, yeah.
Are you taking questions as we go along?
Sure, because I'm really, yeah.
It makes a more lively presentation. It seems to me that each of those is 2 questions.
Okay.
So,
okay, but then I'm going to have to say they're not each a discrete set of 2 things, namely questions. They're each a post-set of questions, because the one question presupposes the other. Yeah.
well, I think they're separate. We can ask what are mathematical objects independently of how we come to know them.
You can.
One is ontology and one is epistemology. So.
Yeah, you can, and myself in my own writing or my own thinking, I spend a lot more time on what are they than how do we come to know them. But I think an answer to what are they, again, it just can't make any sense if it doesn't include some glimmer of how we get to know them. I mean, you can't really answer either question without the other, even though I spent a lot more on the first one. Oh, and I know lots more about what a solution to a PDE is than how to find them. I can't find them at all. Aristotle tells us existence is said in many ways. There are many senses of exist. There are many senses of solution to a partial differential equation. You can talk about smooth solutions or sufficiently differentiable. I'm not picking nits between has derivatives of all order or enough derivatives for the equation. Symbolic solutions are a completely different thing. Well, not completely different, because the symbolic solutions had better be at least piecewise sufficiently differentiable solutions, but it's a different animal. For one thing, I mean, something I think philosophers take way too seriously is the amount of mathematics that's currently being done on Mathematica and similar software. Mathematica knows about symbolic solutions to partial differential equations. Mathematica does not know about smooth solutions. It's just not a thing Mathematica can grasp. Then again, there's generalized function solutions, where the solution is not actually a function at all necessarily. It might be, or it might not be, but it's not required to be. I mean, these are very different solutions and more. For MacLean, as for Aristotle, questions of the special sciences are philosophy, coming to grips with the relations between these. Certainly, as a mathematical specialist in PDEs, you're going to learn a lot about how to take generalized function solutions and use them to find smooth solutions. You're likely to learn a lot about which of those smooth solutions can be expressed as symbolic solutions. Symbolic solution means one that's expressed in terms of functions we take as known. Maybe, you can use trig functions. Maybe you could use integrals of trig functions. You don't just prove there is a function. You can express it in some specified, relatively elementary vocabulary. It's a different thing from knowing it exists. as a mathematical specialist, you're going to talk about relating these. The questions of relating them, for MacLean, as for Aristotle, these are just, they're just of a piece with all the questions you can ask about knowledge. They're not the same as the others, and so let me get to that. Okay, they cannot not be philosophy. You can't answer these without caring about what is knowledge, what is true knowledge. And let me put it, to be very clear about this, we got these two questions, or two pairs of questions, or two post-sets of questions, whatever. Yeah. No, it's a good, I mean, you're right. What are mathematical objects? How do we come to know them? What are solutions to a PDE? And I want to be very clear, a mathematician can certainly learn a technical answer to the second question without ever asking the first question. Right? I'm not foolish. It's not that I don't know you can do this. And a typical math graduate student preparing for their qualifiers probably will learn an answer to Q2 without ever asking Q1. That's normal. Then again, a philosopher can learn an answer to Q1 from convention debate without knowing any mathematics. And that's surprisingly normal. It can happen. These things can both happen. But for MacLean, these are both failures of understanding. I don't have this in his published words, but I have it in conversation. And they are, in fact, failures of philosophy. They're failures to sufficiently love wisdom. Now, we all have failures in philosophy. Nobody can learn everything. It's not about saying everybody should learn everything. But to have just an answer to one or the other of these, in print, we have him complaining about philosophers who only think about Q1 and not Q2. I don't have him in print complaining about math students only thinking about Q2 and not Q1. But his book, Mathematics, Form and Function, is to tell you you shouldn't only worry about any one chapter. You should learn what's in the book. We come to Penelope Matty's second philosopher. I hope people are sort of familiar with this idea. She starts at Aristotle. Aristotle was going to describe everything that a well-brought-up young man should know. Everything. Not how to ride a horse, but all the knowledge that you should have. And this is going to start with logic. Well, with the analytics is what he calls them. There was first philosophy. First philosophy was going to lay down the basics of what is knowledge, what kinds of things are to be known. And then the physics, the politics, where he studies the constitutions of various Greek cities, the economics, where he studies how to run a household or a city. Those were all going to rest on first philosophy. Penn takes it that Aristotle thought we should learn first philosophy first and then learn other stuff. I'm not persuaded of that. Aristotle believes that when a young man undertakes to learn philosophy, they should start with first philosophy because they already know a lot of other stuff. This really isn't meant to be the first thing you know. It's meant to be the first thing you learn in a philosophical format for Aristotle. But Aristotle is then going to go on and describe really everything. I don't know how many of you have read his work on the reproduction of sea creatures. He explains how different sea creatures reproduce. And it's really interesting. Scallops, the ones that fly through the shellfish that fly through the water, these are the only sea creature that is not reproduced from their own kind. Did you know that? No, scallops are not reproduced from other scallops. They arise from a kind of red coral that grows on the seafloor. Well, today we say no. They release these clouds of eggs that are nearly invisible, and they settle down into a red. But Aristotle writes about this, and he's not doing it because he doesn't have enough time, because he has too much time on his hands. He's not doing it to make money on the sales. He's doing it because he thinks you should know these things. If you're going to be a philosopher, you need to know these things. But Penelope Matty's second philosopher will avoid first philosophy. She does not want to base her philosophy of mathematics on some conception of logic or some conception of metaphysics. So I think she's somewhat misinterpreting Aristotle. She's free to feel I'm misinterpreting Aristotle. But anyway, I do like her second philosopher, the one who isn't going to do first philosophy, is not going to start with Aristotle's analytics. What do? Sees fit to adjudicate the methodological questions of mathematics. So here we are, see methodological, it's right. what makes for a good definition, an acceptable axiom, a dependable proof technique? And they're going to adjudicate those questions by assessing the effectiveness of the method at issue as a means towards the goals of the particular stretch of mathematics involved, right? Not by some previous philosophical standard, not by some previous system of logic, but by their effectiveness as means towards the goals of a particular stretch of mathematics. Of course, all active mathematicians do the same. You're constantly evaluating some definition you're about to propose in terms of its effectiveness as a means of solving the issue that you mean to address with it. This is something mathematicians do all the time. This is my general concern with Maddie's naturalism. She wants to approach philosophical questions of mathematics the way a mathematician would. I wish she would spend more time talking about mathematicians who do, instead of just the way they would. How about the way they do? Because they do. Some differences of McLean from Maddie. For one, he was much more attuned to the practical unity of mathematics than Maddie has been. Penn has complained fairly. It's absolutely fair. People sometimes say she only cares about set theory, and that's completely wrong. She does not only care about set theory. But she does take UCLA set theory as her case study. I mean, what she really explores is UCLA set theory, not because it's all she cares about, but she has focused on it a lot, and that's where she gets this stress on the particular stretch of mathematics involved. Because she's argued that a branch of mathematics becomes mature by starting to generate its own questions, its own methods, its own answers, not in response to other parts of mathematics. And by this standard, Zermelo-Fraenkel set theory is a very mature mathematical discipline, because they really do generate their own questions, not concerned with the other mathematics. By this standard, for example, geometry is a very immature mathematical discipline, because geometry takes questions from all over the place and methods from all over the place. Number theory, also a very immature branch of mathematics. I think it's a bad criterion of maturity, but it's the criterion she wants to stress. Whereas McLean was much more attuned to the actual unity of mathematics. It's very easy to find mathematicians complaining that math has gotten so abstract now that nobody can understand the whole field, and it's all fragmented. I think this is a complete misunderstanding of current mathematics. You read Barry Mazur, you read Raoul Bott, you read Jean-Pierre Serre. They have very unified conceptions of all of mathematics. It's not to say they know the details of every branch of mathematics. It is true that no one can read every math book published in a year today, whereas you could have in 1700 if you'd wanted to. But mathematics is, in fact, very unified. And philosophers who don't realize that, well, they should read more and find out it's true. McLean, he didn't just see fit to adjudicate these things. This is something I was just talking about with Steve that I think we've badly underrated as the importance of this in McLean's career. He was explicitly called on by the government to report on the effectiveness of research and teaching methods during World War II and afterwards. In World War II, it was a very pressing concern. How can we get the most out of our investment next year? You know, we need this to be working now. But then on into the 50s, as he's working with the National Academy of Sciences, on various presidential commissions. I mean, it wasn't just something he chose to do. He's called on to go and evaluate mathematics as a whole, and he writes these reports on it that are worth seeing. This is something I wish that philosophers in general would do. I was at a talk a while ago, someone was discussing the ship of Theseus. You know this thing? Greek hero Theseus, he's got this ship, and he replaces some boards, and then he replaces some more boards, and every time he replaces them, he throws the old ones in the river, and they float downstream, and these people pick up these boards, and they build a ship that turns out by chance to look exactly like the original. So which is the ship of Theseus? You know, one of the most common reasons that shipping companies go to court is to establish the identity of a ship, because ships are constantly being rebuilt. You cut it in half, you put the middle of another one in between, and it makes a very great difference where it was built, because Which union regulations you have to follow depends on where the ship was built. Which taxes you owe depend on where the ship was built. So people are constantly arguing this very question for real. And I do not claim that those legal questions must solve the philosophical question. But I do claim it's just really odd to look at the philosophical question without ever looking at the people who actually answer that very question. I mean, we should. Again, I'm not going to claim that by MacLean writing these reports, he settled all the problems of what matters in math. But he made a stab at it, and it's worth seeing. You ought to see it. And most important, he was also called on to assess proposed goals, not just methods towards reaching a goal. And now, in Penn's case, there is a goal, which is to settle the status of the continuum hypothesis. George Cantor makes a really crucial, brilliant decision. He says, I'm going to call two sets the same size if you can put them in bijection. Bolzano had looked at this. Galileo had looked at it. People had said, this is nuts. It just leads to places that make no sense. We're not going to do it. Cantor says, I don't care how nuts it looks. I'm going to do it. I'm going to stand by this. First hard question, are all non-finite sets the same size? He didn't think they could be, couldn't prove they weren't. And he finally proves they're not, because the real numbers are bigger than the natural numbers. Wow. This was hard, and his original proof, although it still finds applications in topology today, it is not the little proof we all see now using power set. You know, it was a much harder proof. Second question, the second question Cantor asked, is the continuum the next bigger size than the natural numbers? This is an open question today. Cantor's second question is an open question today. And that's the question for the Cabal group. That's the question that Penn is studying. She's got a question. They've got a goal. But in most of mathematics, you don't have one goal. In fact, you have to pick what's going to be a goal at all. It's not obvious what should be a goal, either in research or in instruction. And Saunders wrote about both. And I do want to stress, not that it, again, not because it's decisive philosophically, but it is the case that Saunders didn't just decide to address both. Saunders was tasked with addressing both repeatedly by people who required a report at a certain time and were going to evaluate that report. So I just think we should know about these facts. Mathematics for MacLean was not a branch of engineering, but a part of philosophy. By a branch of engineering, I mean, if you're an automotive engineer, and you're told, we need a subcompact car with roughly these parameters. What can you do about fuel efficiency? You've got a goal. You've got to maximize fuel efficiency given those parameters. To a large extent, which is also not entirely realistic, but to a large extent, the engineer, the goals are assigned. And the question is only how to meet those goals. But this is not the case for mathematics on Saunders' level at all. The goals are not assigned. It's up to you to find the goals. Well, any of us, well, we've all been graduate students, and many of us have had graduate students, right? Dissertation, you have to pick a goal. There might be a goal assigned, but. So this is philosophy. Not just meeting goals, but choosing goals, but in both research and education. Now, Saunders did mix exposition with research throughout his career, already in the 30s. He's writing, notes on how to run a logic club for your graduate students. You know, in the 1930s, when it was not a bit obvious what you would have them look at, how to do that. I'm not sure how much people know about his background. I'll be getting back to that. But Saunders was drawn into advanced mathematics very largely by logic. It was a major part of his motivation. And when he comes back to the US from Göttingen, I do enough history of math to point to the dates here. I first know him saying 50 years later that he decided there's no jobs in logic, there's jobs in algebra. So as a historian, I'll say, okay, I don't know that on paper before 50 years later, but I believe it absolutely. I mean, this is also part of the job of the historian. Is this a plausible claim? I think it's probably exactly true that in the 30s he looked around. He didn't even have to look around. He could have asked his advisors, and they would say, logic, I don't know what that is. Algebra, I know what that is. But he was choosing consciously right then whether or not to specialize in logic. And I want to compare that to what Aristotle says, because we don't always hear this about teaching. I didn't know Aristotle said this until I was looking for quotes for this. In general, the sign of knowledge or ignorance is the ability to teach. So we hold that art rather than experience is knowledge. Some can teach, some cannot. Those who can do, those who really know what they're doing, teach. It's a little different from the slogan we sometimes hear. And that was certainly Saunders' approach. And this, to me, is the greatness of his book, Mathematics, Form, and Function. If you haven't heard of it, well, you've heard of it now. I should have put the name up on the slide. But I asked him when it came out. This was about 1985, 87. I don't remember the exact year. I asked him, is this your account of the math that philosophers ought to know? Now, I'll tell you another thing I've learned as a historian. Never ask a person a yes-no question. Because if you ask them a yes-no question, they will try to tell what answer you want and give you that one. Okay, if you want to bias the inquiry, use yes-no questions. But if you're really trying to find their opinion, it was a leading question. But what he said to me was yes. Mathematics, Form, and Function was, on one hand, it's meant to be an exposition of mathematics for philosophers, so that you'll know some math instead of not know any math. The way it got used for a long time, and I'm not sure it's even being used, most of the sales apparently were to math graduate students using it to prepare for qualifying exams. They thought, here's an overview of lots of stuff, and I'll understand that. But the point of it was meant to be to present mathematics as a whole for the purposes of philosophers. Saunders could teach, that's for sure. And also I will mention here, Aristotle, here this knowledge is episteme. That's the highest praised term for knowledge. This isn't just somehow knowing something about it. This is, they say modern translators often render it scientific knowledge, which is not really good Greek philosophy, but it conveys to a modern audience. So this is not what Plato would have written, right? Plato would not have talked about art this way. Aristotle's theoretical demand on philosophy was a practical demand in mathematics for MacLane, and I think Aristotle meant this to be. I think Aristotle's theoretical demands of what philosophy needs to be were meant to be the actual demands of what physics had to be, and what politics had to be, and what economics had to be. It was meant to be what the special sciences need to do. And it's exactly what mathematics needs to do for MacLane. Again, we do not think we know a thing until we're acquainted with its primary conditions or first principles, have carried our analysis to its simplest elements. I'll come back to that in a way. But yeah, knowledge, episteme, this kind of knowledge is understanding. It's not just accumulation. It's better than, and for Saunders, mathematics had to be that. MacLane eventually knew the huge profusion of mathematics and the deep unity of existing mathematics. Something I wish philosophers knew both. Philosophers will often talk about how math is so broad and diverse and nobody can master it all. But even the people who stress that, I think, I wish they knew more about the actual breadth. I wish they knew more concretely how very broad mathematics is. It's not that I think everybody needs to be researching all these topics, but I wish it was just better general knowledge. But at the same time, that broad profusion is deeply unified. Again, just to use some names, Raoul Bott. Raoul Bott, to my knowledge, never writes about the unity of mathematics, but when he writes about mathematics, it's an utterly unified vision of it. Jean-Pierre Serre real French speakers, when they say "ser," it's wonderful sounding. I can only come close. When he writes about mathematics, he doesn't even present a unified picture explicitly in the writing. Any one sentence is about one topic, and yet, when you read a stretch of him, there's a very unified thing coming out of it. When you read summaries of his research, vastly unified. I do wish that philosophers knew more about that. Well, Saunders did know about that. I'm not sure what he thought about Serre's work. Well, we don't need to argue about that. But I do want to stress eventually, because when Saunders began as an undergraduate, he talks in his autobiography, well, we could worry about the authenticity of the autobiography also, but about his discovery that mathematics was something you could actually learn for a living. You know, he knew you could take it in classes, but he didn't know you could do it for a living when he was in grade school. When he learned, by the time he's going to college, he wants to know what's in this Philosophia Mathematica. There's this new kind of math being done. It involves logic, it involves algebra, and it's made everything new, and he wants to learn it, and he wants to be part of making everything new. At this point, of course he doesn't know very much, right? He's just enrolling as an undergraduate. But he wanted to learn Philosophia Mathematica because he thought this was the way to do math. We're really going to do it this way, and we're going to learn a lot more by doing that. He goes to Yale. Oh, I'm blanking on the exact order of his. He got some education at Chicago also, right? Besides, yeah, I don't remember the details of that right now. But the advice he gets in both places is, well, okay, in Yale, I know what happens. In Yale, he goes to his advisor and he says, I want to do an honors thesis on Philosophia Mathematica, or Principia, Philosophia Mathematica. Russell and Whitehead, Principia. Yeah, I just call him Russell and Whitehead. He wants to do a dissertation. He wants an honors thesis on Russell and Whitehead, and his advisor says, "Oh, I don't know. I don't think that's a really good idea. You should do it on Hausdorff's topology. Yeah, you should do it on Hausdorff's topology." Mengenlehre. Well, yeah. It's called set theory, Mengenlehre. And half of it is point set topology. And his advisor says this, and this is already a crucial difference. He's being steered away from logic and philosophy of math into doing a little bit more math. And he learns that. But then he wants to get in on this algebra stuff that he's heard is important, and he's heard that there's this Emmy Netter in Germany who's really good at algebra. And so maybe he should go there. And where is she? She's at Göttingen with David Hilbert. Okay, think, shall I learn from David Hilbert? Yes. So he goes to Göttingen. He gets there in 32, I think. Is it possibly 31? 32, I think. Not a great time to get to Göttingen. But it's when he had. He hears Hilbert giving weekly lectures on philosophy. Hilbert has retired, I believe has retired, or is just about to retire. And he's giving his retirement lectures for the broad academic public, right? I mean, he's not going to a working man's society, such as you might have had in London. But this is the public. These are public lectures on mathematics and philosophy. And he learns Hilbert's epistemology of math, which is very brief. It is not what we would call an articulate theory of epistemology. Wir müssen wissen, wir werden wissen. We must know, we will know. In math, he actually doesn't say in mathematics there is no ignorabimus, there's nothing we won't know. He says for us mathematicians, there's nothing we won't know. And I believe for the sciences overall, meiner Meinung nach, für die Wissenschaften überhaupt. An epistemology of pure optimism. Like I say, this is not a detailed epistemology, but it's got a clear conclusion. There's nothing in mathematics we won't know. To me, this does not contradict Gödel's incompleteness theorem. He's saying there are no mathematical questions we can't answer. Questions we can frame, we can answer. And he specifies, Hilbert specifies in his logical investigations, to take the obvious case, the axiom of parallels. We must either prove the axiom of parallels, or refute the axiom of parallels, or show that it is not determinate on the current data. These are all solutions to the problem of parallels. And in that sense, there is nothing we won't know. Gödel's incompleteness theorem may be shocking, but it's something we know. We do know it. And Saunders, I think, always had that optimism. Personally, I had that optimism even before I met him. I believe I was a little surprised when the four-color theorem was proved in my lifetime, and stunned when Fermat's last theorem was proved. But not because I don't think it'll happen. I think all those things will happen. From Hermann Weyl and Moritz Geiger, he actually talks with them about philosophy. Weyl has already written his philosophy of the natural sciences. I forget the exact title, but yeah. And Weyl is already revising it. Saunders Mac Lane rents a room in Weyl's house and talks about this with him in the kitchen.
He translated it into English.
Yeah. But not the translation that got published years later. Yeah. And when I asked him about it, he said he just had no memory of how similar they were, which I think is probably true. Moritz Geiger was a philosophy professor who had been hired on Hilbert's. Hilbert had first gotten Edmund Husserl hired. This was against much opposition from the philosophers on the faculty, but at this time, the entire faculty voted on all appointments, and Hilbert got Edmund Husserl hired. It's clear, and you see this even in Rudolf Carnap, for mathematicians at this time in Germany, and even for Carnap, philosophy meant phenomenology. And Carnap's, when Carnap talks about, he gives his criterion of meaning, he says there are four ways you can understand meaning. There's the traditional way, I forget, but one of the ways he calls philosophy, well, in German, Philosophie, and in parentheses, phenomenology. He uses phenomenology as a gloss on the word philosophy. That's what philosophy is for him, is phenomenology. And phenomenology at this time is obviously not Heideggerian phenomenology. It's a phenomenology that says we have different levels of experience that involve different notions of existence. We want to look at all the different levels of experience, not try to decide that one is right and the other is wrong. We want to compare all of them. And he gets that philosophy from both Weyl and Geiger. And he gets from both of them that mathematics is a science of forms. Mathematics deals with forms, which could be forms of physical systems, but might not be. Somehow forms are, well, Geiger promised us a second volume. This is something he has in common with the topologists. You promise a second volume and it never appears. In his English book title, Mathematics, Form, and Function, well, what he heard for a whole 2 years in Göttingen, because when he went to Göttingen, he's there to get a doctorate in mathematics. And every doctorate in Germany at that time includes an examination on philosophy. It's just part of the program. So he's examined on Geiger's philosophy. And it's a philosophy that says mathematics is a science of forms. And Geiger tells us this, but Hermann Weyl tells us much more clearly. The reason it's a science of forms is not because somehow we sort of think so. It's because that's what makes it work. That's what lets us prove theorems. It's when we regard it as a science of forms, we don't get lost in a lot of complications, and we succeed at proving theorems. Also, that's what makes it possible for students to learn. Even just to teach imaginary numbers. If you're going to try to teach imaginary numbers by telling your students what a square root of -1 is in some philosophic terms, you're just wasting their time. No, you teach them complex imaginary numbers by showing how to calculate with imaginary numbers, proving the basic theorems on complex analytic functions. That's how you explain the imaginary numbers. You show their form, you don't worry about what they are. He does learn this phenomenology. He does not adopt phenomenology himself. I do not remember him ever using the word phenomenology. I don't think he was aware of it at all. His descriptions of his philosophy make sense when you put him in the US context in the 40s and 50s, which is only good sense, right? He's describing philosophy the way the people around him are describing philosophy. But he did hear this phenomenology, and he even, studied it for qualifying exams. What is a form? What are these forms that mathematics studies? Well, Saunders tells us at the end of Mathematics, Form, and Function that he's just opened that question. He's not answering that question. Okay, that's good news, because that means you can advise a doctoral student who will answer the question. I don't know. I mean, I've got an answer. Somebody was asking me to do Chinese philosophy. I have published an answer to that question in Chinese. Co-authored with Liu Jie of Shanxi University. She did the writing. Yeah, but, it's a disappointing answer if I put it in a nutshell. In a nutshell, what a form is an object in a category. You put it like that, it doesn't sound very appealing. We got a better way to put it. He's not going to explain what forms are, but the crucial point is forms could be forms of, for example, a physical system, but do not have to be. That's what Saunders is very clear on throughout Mathematics, Form, and Function, and those phrases could have been lifted from Geiger's book. We know what book by Geiger he studied with Geiger in order to pass the qualifiers. So you can, oh boy. When I first went to graduate school, if I'd heard of that book, I could have spent 6 months trying to get a copy. Now I spent 6 minutes getting a copy. It's better today. And from Noether, he learns algebra as the future of mathematics, something he was already prepared to learn, but there's a lot I could say about Aimé Noether. I've worked on her a lot. To say that all she cared about was algebra, I don't think that's a very good way to describe her view of mathematics, but if you're going to, she believes algebra is all of mathematics. All of mathematics will be correctly understood when it's been made algebraic. And this is not a reductionist. This is not to say forget the other stuff. It's the other stuff will all be defined this way. This is the way to do all of it. And Saunders absorbs that viewpoint from her, not so much the broad sweeping claims, but. And he comes away deeply disappointed with his dissertation. He went there to write a dissertation on logic. He had this idea. You look at Principia Mathematica, you can't really do mathematics that way because it's too long. The proofs are too long. And he says, I'm going to shorten it. What I'm going to do is a lot of the steps are repetitive, so I'll come with shorter versions of those steps. And then with those shorter versions, it'll be feasible to really use this stuff. And he writes a dissertation defending this claim. And he's embarrassed about that dissertation for the rest of his life. And he did. It's not that it's bad work, but it's wrong. It's wrong. One of the things I learned from looking at that dissertation, he shows how to take this logical approach and cut it down to 10% the length. But it turns out that reducing by a linear factor is unimportant. This is something that the computer scientists already know. Changing complexity by a constant factor is completely unimportant. You have to change it by an exponential in the length of the input or something like that. The right way to abbreviate mathematics is not to routinize the definitions you use most often. The right way to abbreviate mathematics is to find compelling dissertations, compelling definitions for each new concept. There's not going to be a routine for abbreviating mathematics. It's going to be the extremely non-routine exercise of finding the best concepts each time. He comes away very disappointed in his dissertation. This is not going to work. And he gives up, he loses all faith in philosophically motivated philosophies of mathematics. Yes, there will be no purely philosophical philosophy of mathematics. This will always lead you wrong. Because Russell and Whitehead gave a beautiful case for their philosophy of mathematics, Russell's, really. And as Russell realized by a decade later, it was wrong. It's not the way you can actually do math. So Saunders is not going to be any purely philosophical philosophy of mathematics. Then there's what he learned during World War II. Again, I think we badly, I say we. Me, I did. Oh, I was not even aware of that, what all he did during World War II. I think to understand Saunders, we really need to do it. And there's two things he does during World War II, surveying all of mathematics for the government, but also looking at fundamentals of algebra and topology with the suspicion that this will be all of mathematics, all the way down to foundations with Eilenberg. He does that during the same time as he's doing all these surveys. And in this general theory of natural transformations, natural equivalences, general theory of natural equivalences, there is a little section on foundations where he talks about which set theories would be adequate. And of course, he talks about set theories that exist. I am sometimes dismayed at people who said, Saunders Mac Lane used standard set theory for a foundation. Well, yeah, because it existed, right? I mean, he used ideas that existed. This is all at the same time. Where did this leave foundations? After his dissertation, Mac Lane never believed we knew the absolute simplest elements in mathematics, and here I'll mention Steve and his case against foundations, which people don't always recall. But it's a clear case. I believe a clearly mistaken case. Okay, I disagree with Steve about this. But let me advertise the importance of his case, right? Read the case. And Saunders certainly did not believe we know the absolute simplest elements. I don't think that Saunders was against foundations per se, but he certainly thought if there's going to be a foundation, it's going to be for now. It's never going to be an absolute foundation. Lavier's set theory as endoxa, bringing us back to Aristotle. Endoxa are those opinions that the better sort of people have and that stand investigation. Saunders became a great champion of Lavier's set theory, not because it was a new way of looking at sets. For Saunders, Lavier's categorical set theory is the opposite of a new way of looking at sets. It looks at sets the way mathematicians all did by 1960. Only it does it thoroughly, it formalizes it thoroughly. This is what we already knew about sets. Unlike Zermelo-Fraenkel, which involves lots of sets that lots of stuff that most of us never learn at all, Lavier's set theory just uses the stuff that we all already know. And that's the point of it for Saunders. Not that it's radically new, just the opposite. It's what we're already using. He's just made it precise. And Saunders never saw that as very different from the category of categories as foundations. In one way, it's very different, but he didn't see it. Questions of truth and beauty are essential, both for a concise overview of math and also for the future direction. Can philosophers decide the future direction of math, which he raises in mathematics, form, and function? Are you kidding, philosophers? Only philosophers can ask it. But philosophers doesn't mean only people in philosophy departments. For Saunders, this is a paradigmatically philosophic question, and mathematics depends on answering it. That does not mean that the philosophy department are the specialists. Saunders did not want philosophers to kid themselves about how much they knew. Saunders, incidentally, didn't want other mathematicians kidding themselves about that either. Saunders fairly often took me to task for not knowing enough, but he never took me to task for having the wrong degree, right? It's just a question of how much do you know. And that's where I've got. Yeah.